Okay, so today we're going to be talking about data structures. So this first chunk or section of the lecture will just give an overview of data structures, kind of what they are, how they work, and some very common ones that you should know about. So what are data structures? Well, they are the way that you organize your data. So there are lots and lots of different ways to store and utilize and organize data, and every particular way of doing it has its own strengths and weaknesses and its own use cases where it shines or it's a bad choice, right? Just like any other tool, um, you can unscrew, you know, you can unscrew a screw with a dime, maybe, but it's better to use a screwdriver. Maybe you can unscrew a Phillips head screw with a flathead screwdriver, but um, you know, overall, it's best to choose the right tool for the job. And when you're starting out, uh, that might not be an easy thing to do. But as you get better, you'll start getting a better sense for how this works. So why are data structures important? Well, they make your software more efficient. So especially when you start scaling up, this is an issue. If you're just doing a small personal project and you're using small amounts of data, these kinds of questions might not be so important, but uh, as you work on things that are bigger and bigger and bigger, small inefficiencies can add up. So, being able to choose the right data structure is important. Okay, so here are just some common on the right here, some common data structures. There's arrays or lists, objects or dictionaries. There are stacks, queues, linked lists, and then various kinds of trees. Um, so some of this stuff gets a little bit more complex, but so we should already be familiar, at least in general, with arrays and objects. But we'll talk more later today about stacks and queues and linked lists. But for now, we're going to actually focus on why might you choose a particular data structure. So there are a lot of different reasons for choosing one data structure over another. I just want to bring up one that maybe doesn't get very much attention, but it's something to think about. So, for example, um, choosing a data structure that is more maintainable or more readable or understandable to other humans. So there are issues of efficiency and so on, but there's also a human element. Coding is a collective social enterprise. Whether you like that or not, that's just kind of how it works in practice. So if we have a bunch of user objects in our application, and we just have all of these values, and we create another user object, and we just have to make sure to line everything up. But if I just look at this in isolation, like I can probably guess that this is a name, and maybe that this is an age, probably that this is an address. This I have absolutely no idea. So one solution to this is just to maybe add like a comment here, and we can say, this array, the first one is name, age, address, and married or is married, something like that. So that's a possibility. But if we imagine that this is not just 4 things, but maybe 10 things or 20 things, it starts the likelihood of someone making a mistake just goes up. So we might choose a different structure, not based on, strictly speaking, the needs of the application, but just based on uh, maintainability questions. So what are people going to find easier to understand and use? So here we take this array and we turn it into an object. And now any human can look at this and see what a user is composed of. And if they want to make a new user object, it's much clearer and much less likely to lead to errors. Okay, so that's just one consideration for maintainability. Okay, so let's take a look. We mentioned a few data types. array, objects, stacks, queues, linked lists. So let's talk about some of these that we maybe haven't seen so much. So stacks, we've seen the call stack. So we kind of know what that is. You can visualize it in the debugger, right? So as you're running a bunch of recursive calls, for example, you can see the stack kind of pile up, and then once you hit that final value, the stack starts unwinding or popping things off of the top, and it gradually goes down to zero. So a stack is a data structure. It's a particular way of organizing data, and it's the acronym is LIFO, last in, first out. And the way it works is just like a stack of plates at a buffet, right? So you have a stack of plates, and if you put a new plate on, the plate you take off will be the plate that you just put on, right? So the last one in is the first one out. And a queue, on the other hand, so a stack only has one access point. So you can only put things and take things off from the same place. Queues, on the other hand, have two access points. One to add things on, so you can add them from the back or the bottom, basically, and you can take them off from the top or the end, depending on if you're thinking about this vertically or horizontally. So a queue operates the way we like a line to operate, right? I got here first, so I'm the next person who's gonna be able to order a sandwich or whatever. And the guy who got in line after me, who's behind me, he's gonna have to wait until I'm done before he can do his thing. So there are kind of methods that we associate with these operations called onqueue or dequeue, and if I'm, these might be pronounced differently. So, but in any case, onqueue puts something into the back of the queue, and then this thing is going to gradually work its way up to the top where it'll be dequeued in order. Stacks, when you put something onto the stack, it's usually called pushing. So I push it onto the stack. When I take something off, pop. So push, pop versus onqueue and dequeue. Linked lists are a little bit more complicated. So data structures can be relatively simple or relatively complicated, like anything else. And when we get to linked lists, we're starting to get to the more complicated area. So a linked list is going to be composed of these elements called nodes. And a node is going to have two features. So a node will have a piece of data, which is maybe the thing that we care about, but it's also going to have a reference to a neighboring node, so to one neighboring node. So why might you do this? Well, if we have a bunch of data, so this data could be a number or a string or an object or whatever happens to be, but it needs to be connected to something else so that we can go through the chain, right? So we need to be able to start at the beginning and go through a linked list, and we could search for something, we could add something on to our whatever we're trying to do, but it's a more flexible structure in a lot of ways. But there's a trade-off, right? So we're increasing complexity, we're increasing memory usage because we have to store two things for everything we want, whereas on a stack we don't really need a reference to the next node or anything like that. Okay, so let's kind of examine a case study of arrays versus linked lists. So arrays and linked lists have a lot in common, but there are also some basic differences, and that might be appropriate to use one at one time and another at another time. So here we've got just a little diagram. So here are some of the features of a list or an array. So it's arrays are good, or lists are good for indexing an element at a specific index. So if I want to be able to immediately access any given value in a data structure, then an array is a very good choice, because basically the memory address of the first item of the array is stored, and arrays, at least actual arrays, are organized as contiguous blocks of memory. So you have all this memory on your computer. When you create an array, you're carving out a contiguous block. So if I want to access the fifth element in the array, all I have to do is I know the memory address of the first element, so I just have to add 5 to it, and then I don't have to go through every single item in the array. I can jump immediately to wherever I need to go. So you get immediate access, or O of 1 access to any given element. If we look at a linked list, for example, because this is just a chain, and if we look here, this middle node right here, it only knows about the node right next to it. It doesn't know anything about the node before it. Doesn't know anything about the node 5 doors down. There's no direct way to jump around. So if you want to look for something, then you have to look through you have to follow the chain. There's only one path through the data. That's it. So the downside, so all of this is trade-offs. So some positives, some negatives. So lists, for example, or arrays, are slower at inserting elements in the middle or beginning. So because a list is a contiguous block of memory, if I add something to the end, I can always, let's say, assume or hope that there will be another free piece of memory that's right next to my current array. Or what actually happens is when you create an array, Python or whatever you're using will actually create an array that's larger than what you tell it. So it leaves room for you to add to it without having to potentially find a new home of contiguous memory space. The linked list is fast at inserting. So you can add something to the beginning of a linked list in O of 1 time. So it's meaning that you can do it immediately, right? So if I add something to the linked list, I can add another thing right here, and all I have to do is basically point whatever new data I add. I just have to have the next node equal this one. So I don't need nothing else in my linked list has to change. I just need to mess around with one of the nodes, basically. Whereas with an array, I may need, if I insert at the beginning, I'll need to shift everything over. So I basically need to recreate the array. So it's slower. So it's O of n times. So if I have 10 things in my array, then I have to do 10 operations to shift everything over. Okay, so let's take, this is more of maybe for the sake of novelty, but I think it's interesting. So Python offers you some good tools for introspecting. So we can see, let's take a look here. And you can use something called ID. So there's a built-in function called ID, which will give you the memory address of whatever you pass in. So we create an array called myr, 1, 2, 3, 4, 5, and then I print the ID of myr, and it gives me this long number, which is an integer representation of a memory address where this lives. And if I run this application again, I'll get a different value, because whatever happens to be happening in my computer at the moment is going to be what I get. So I can't rely on this being a number. So every time I run the code, a new, it's going to find what it finds. All right, so I have a thing. So I have an array. I know the memory address. So let me go ahead and append something else. And notice what happened. I have my array, right? 1, 2, 3, 4, 5. I append something else onto it. So you might think, okay, we're going to get a new, it's going to be a new thing, right? But it turns out that it's not. So because we're appending to the end, the original, array or the memory address will be the same. So that's just something to keep in mind for arrays. Now what we can do is print out all of the memory addresses, print out the memory addresses for every single item in the array. So let's see what we get there. Okay, so we got this, and then notice what's happening here. If you, if you take the time to count, you'll see that this increases by 32 every time. So 32. So Python is allocating 32 bytes to everything in this array. So these are contiguous. So if I start from any given array, I can add 32, and then I can go immediately or whatever. So if I'm accessing the fifth index here, I can start at the first one. I can do 32 times 5, whatever index I'm doing, and then go immediately to the thing that I want. So here's another interesting trick. So I'll just go ahead and run this. So what we're doing here now is we're getting the memory address, and then we're using a built-in C type. So Python, a lot of actual Python is written in C. So in C you can have pointers and all kinds of stuff. But so here's a built-in something from a standard library that allows you to play around with some of the lower level stuff. And we can actually access the value. It's almost like using a pointer. If you don't know what that is, that's fine. But this is almost like using a pointer. So we're taking the memory address, and then we're getting the value at that particular memory address, which in this case is stake. So we have this array with 0, 1, 2, 3, 4, and then the fifth element is stake. So what I do is I grab the ID, which is going to be this number, which is a memory address, right? And notice that it's it's actually different here. So there are some issues with how Python actually implements arrays. It's not quite as simple as what I've been telling you. So arrays as an ideal are quite a bit stricter than what Python actually implements. But this is an illustration of kind of how it works. So you can get a sense of what the memory situation is. All right, so let's talk about, so now we have a good idea of what a linked list is and what an array is. So let's run through this example just to show you, why you might want to use an array versus a linked list. So here we have an array, and here's a visual representation of your memory. So just a bunch of contiguous slots. So we create an array, and we put all of the elements in the array in these contiguous slots. So that makes it easy to access an arbitrary element in the array. Okay. Okay, so let's say we have this array. Let's say we add another thing onto the array, but there's something occupying that space, right? So we created an array. Python allocated a certain number of slots for us, contiguous. It found a bunch of contiguous memory. It stuck our array there, but then we want to add something, so Python has to find the next contiguous space in memory and try to add that value there. But what if that space is already occupied? So then it can say, okay, well, let me find another free spot. So copy all the values, move them around to the new spot that has enough contiguous memory. So that could be an inexpensive operation. Okay, so what happens if you have an array, and maybe it's a very, very large array, and there just isn't enough contiguous memory to hold your array? Well, then you could have an error. So if this were, again, like the way this is actually implemented in Python is it's not quite this straightforward, but if we think about linked lists as a solution to this problem, a linked list, elements, because all of these nodes are independent units, they can be anywhere. They can be anywhere in your memory. And because they have a reference to the next node, then they don't need to be contiguous. So there's no real spatial requirements for storing a linked list. So we can have this head node here, right? And that can refer to this other node that's way over here. So it doesn't really matter what else is going on. So we start here. If we want to move to the next one, we go to this memory address, right? And it's the same thing. So we can have this very chaotic distribution in actual memory, but from a user interface perspective, like an API perspective, it's very clean. So we start with a head. We can go from one node to the next. So that is the basics of data structures. We've looked at stacks, queues, and linked lists primarily. And in the next little chunk, we'll go ahead and implement each of these data types.